Hi, hello, good evening everyone. Welcome to India's largest e-learning platform, Gradeup, and welcome to the session 25 most important topics. Today I will be discussing the very first topic, that is AVL trees. Are you all ready? Join the session quickly. Quickly share it to all your friends. Ask them to join live. And those who have joined, please mark your presence. Good evening, Lalit Kumar. So before I start, let me introduce myself quickly. I am Satya Narayana, research scholar with 13 plus years of teaching experience and all the other credentials. I teach computer organization and architecture, computer networks, operating systems, data structures, and algorithms. Okay. Anusha, Sandhya, Srishti, good evening. So shall we start? Siksha Pandey, good evening. Students, please reply. Shall we start? All right. So AVL trees, definitely one of the most important topics, and this is the topic from programming and data structures. Swaroop, it is good if you can practice the last 20 years papers. In the worst case, at least last 15 years papers. Okay. So AVL trees, which is the most important, one of the most important topics in programming and data structures. Now let us understand AVL trees. Before that, let me tell you what is binary search tree. Before understanding AVL tree, first we have to understand what is binary search tree. Santanu Sahu, very good. You are correct. Yes, Lokesh, I am going little slowly. Let every one of the students join. Okay. So what is a binary search tree? It is a binary tree. What is basically a binary tree? Where the maximum number of children for any node is 2. That means any node may have 0 children or 1 children or 2 children. Maximum is 2. So a binary tree in which parent node is always greater or equal to its left child or left subtree and smaller or equal to right child or right subtree. Whenever we find this, then you can say that is binary search tree. For example, if I take one tree like this, 70, 40, 20, 60, 82, 75, 87. If you observe this, 70 is greater than all its left subpart, and smaller than all its right subpart. Similarly, 40 is greater than 20, less than 60. 82 greater than 75, less than 87. So, all the left subtree should be, for every node, it should be smaller. All the right subtree, it should be greater. Then it is binary search tree. I'll give you one more example. So here it is satisfying. So it is a binary search tree. Yes, Srishti, very good, very good. Suppose if I have a tree like this, 70, 40, 20, 30, 82, 85, 87. Carefully observe. When you compare with 70, all the left are smaller, all the right are greater. But this property should be satisfied at every level. 40 is greater than 20, but is it greater than 30? No. 40 is greater than 30. 40 should be less than 30. Similarly, at 70, 82, 85, 87 are greater. At 70, the property is satisfied. But 82 left should be smaller than 82. But 85 is greater than 82. So here it is not satisfied. So guys, at every level it should be satisfied. So the second example is not a binary search tree. Srishti, what Sheikh Umar is telling, that is true. We can place on either side, but whatever we select, left or right, we will follow the same throughout the tree. Throughout that tree, we will follow the same. Okay? So I hope what is binary search tree, this concept is now clear. Now, before we go for these things, the AVL tree concept, let us make what is the height of the binary tree or binary search tree also. The length of longest path from root to leaf. This is the formal definition of height for the binary tree. In general, we will start counting height with 0. Height counted from 0 generally, but let us consider the height is numbered from, let us consider the height we are numbering from 1. Okay, height we are counting from 1. So suppose if I am taking a binary tree like this, A, B, C, D, E, F, G, H, I. Now, first, what is the height of I? We are counting the height from 1. Okay, please remember this. Generally, we don't count from 1, we will count from 0 only. Now, we are counting from 1. So, I is at height 1. H, its child height plus 1. So, H is at height 2. G is at height 3, F is at height 4. Now D is at height 1, E is at height 1. Now whenever we have two children, maximum height of the children plus 1 will be the parent height. So C height is 2, B height is 3. Now A is having left child B at height 3, right child F at height 4. So which is the height of A? Maximum of the heights of the children, which is 4. So we say A is at height 4. So what is the height of the tree? We say height of the tree is maximum of heights of all the children or all the nodes. Obviously the height of the tree we can say, sorry, A height is 5. Height of the tree we can say is 5 here. Again I am reminding you, we are starting the height from 1. From 1 we start in this context. Okay. So now what is height? Clear? Now one more thing we have to understand before AVL tree, that is what? Balance factor. What is balance factor? Means the height of left subtree minus height of right subtree, or height of left child minus height of right child is called balance factor. Suppose I am taking a binary tree like this. Suppose this is the binary tree. Now let us calculate the balance factors. Remember, balance factors of all the leaf nodes is always 0. Balance factor of leaf node is always 0. So D balance factor is 0, E balance factor is 0, F balance factor is 0, H balance factor is 0, K balance factor is also 0. Now C balance factor, C left child is at height 1, D is at height 1, E is at height 1. So C balance factor would be left child height minus right child height, that is 0. Now J balance factor, J has no left, so the height of left child is no left child, so 0 height. Right child is at height 1, K is at height 1, so 0 minus 1 minus 1. Now I balance factor is I left child J at height 2. What is the height of J? 2. And is there any right child for I? No. So this is 2 minus 1, 2 minus 0, 2. 2 is the balance factor for I. Then B balance factor, left child C is at height 2, right child F is at height 1. So 2 minus 1, 1. Now A balance factor, left is at height 3, B is at height 3, D height 1, C height 2, B height 3, minus right. Okay, before A, let's find G balance factor. H is at height 1, right side I is at height 1, 2, 3. So 1 minus 3 minus 2. Now A balance factor, left subtree is at height 3, right subtree is at height 4. So 3 minus 4 minus 1. So got it? What is balance factor? Left subtree height, left child height minus right child height. That is called balance factor. Okay. Now the nodes whose balance factor, the nodes whose balance factor is other than -1, 0, +1, such nodes are said to be critical nodes. What we call such nodes as critical nodes. So I will be mentioning the critical nodes with star. So what are the balance factors of A, B, C, D, E, F, G, H, I, J, K? A, B, C, D, E, F, G, H, I, J, K. A balance factor is -1. B balance factor is 1. C balance factor 0. D balance factor 0. E balance factor 0. F balance factor 0. G balance factor -2. H balance factor 0. I balance factor 2. J balance factor -1. K balance factor 0. So which are having the balance factors other than 0, -1, +1. G is having the balance factor -2. I is having the balance factor 2. So here what are the critical nodes? G and I are critical nodes. Okay. So I believe you understood what is binary search tree, what is the height, what is balance factor. Right? Now let us proceed to AVL tree. What is AVL tree? AVL is initials of the scientists who have invented. However, we don't require them. Leaving that, AVL tree is called height balanced binary search tree. Height balanced binary search tree is called AVL tree. What is height balanced? When all the nodes balance factors are in the range -1 to +1, that means either -1 or 0 or 1, then such a tree is called height balanced. So here for AVL tree, two conditions. One, it should be height balanced. Other, it should be binary search tree. Two conditions should be satisfied. Okay. Why to balance the height? Why? Again you will have a doubt. Why? Why the height should be balanced? Why the balance factors should be these three? The reason is because to reduce the searching time complexity, for a binary search tree from big O of n to big O of log n. For example, let us say I am having a binary search tree. You assume A, B, C, D, E values in this way. Suppose you would like to search for E. how many comparisons you do? Here you will be doing the number of comparisons is equal to 5. 5 comparisons you will do. The same notes, if they are in this way, suppose the same notes if they are in this way, now how many comparisons you do? You will be doing the number of comparisons, only 3 comparisons, because we will match with C. If E is greater than C, we will only search in the right subpart. Left nodes you need not to compare. Why this difference? You see the balance factors. E balance factor 0, D balance factor 1, C balance factor 2, 3, 4. So there are critical nodes, many critical nodes. But here you see the balance factors 0, 1, 0, -1, 0. So all the balance factors are in the range 0, -1, +1. So if you maintain the balance factor in this range -1, 0, +1, definitely the searching time complexity will be less. This is the motto. This is the motto. Okay. Now, if the given tree is not balanced, if the given BST is not balanced, what to do? Then how to balance? The answer is by rotations. By rotations we can balance what? Unbalanced binary search tree to balanced binary search tree. What are different rotations? 4 different rotations can be performed. 4 different rotations can be performed to balance. What are they? L rotation, R rotation, LR rotation, RL rotation. LL, RR, LR, RL. Right? Good. Santanu Sahu, Srishti, Chandana, everybody who are involving in the session. Very good, guys. Very good. Just stay tuned to the session. It is going to be very, very interesting. Now let us see what is LL rotation. Before that, let me introduce our courses. Gear Up, Rank Up, Vision 2022. Vision 2022 is for 2022 aspirants. So it's a long-term course who are in second year, third year. They can attend this. Rank Up, this is completely for practice. Gear Up, this is concept oriented. Majorly we will be discussing the concept in this course, and you can find the highlights of each course. So to access all the classes, take a Gradeup Super subscription. With this, not only the classes of GATE, for all other PSU exams, whatever the course happens in the subscription period, all you will be able to access. Okay. Now, who will teach all these courses? Definitely. Let me present our pool of expert faculty. Mr. Murali Krishna sir with 20 plus years of experience, me with 13 plus years of experience, Mr. Ankit Doila sir with 8 plus years of experience, Mr. Navneet Gupta with 7+ years of experience. Now let us see what is these rotations when we perform these rotations. So first, LL rotation. Guys, always remember there may be any number of nodes. For rotations, we have to identify 3 nodes. I am naming them as A, B, C. You can use any other names. So see this. Suppose we have nodes in this way, A, B, C, left skewed, such that A is the critical node. Obviously, balance factor for A will be other than -101. So whenever A is critical node, because of inserting C at the left, then we do LL rotation. Though it is LL rotation, we will represent with right arrow. So whenever you do LL rotation, B becomes parent, A will be right child, C will be left child. In simple, this is what LL. Now, let me give you the general formula kind how LL rotation is performed. Suppose B is the left child for A, C is the left child for B, A has its right subtree, B has its right subtree, C has its left subtree and right subtree. Whenever we perform LL rotation, what happens? B becomes parent, A becomes its right child. See, at B we are applying the rotation, at A we are applying the rotation. So B comes to A place, A goes to right part. Whatever is attached to A, that will be as it is. Left of B also will be as it is. Now what else we have not counted? Right child for B. As this is right child for B, it will be on the right side only, but left child as left child for A. As left child for A. So this is general formula. Now I will give you one example quickly. Suppose we are having like this 70, 60, 40, 65, 80, 75, 82, 35, 37. Just a moment. $32. Okay, as a left child for 35. Now, if you find the balance factors, if you just find the balance factors, 32 balance factor 0, 35 balance factor 1, 40 balance factor 2 minus 1, 1, 60 balance factor 3 minus 2, 1, 70 balance factor 80, 75, 82, 62, 45, these are all having balance factors 0, 80 balance factor 1 minus 1, 0. Now 70 balance factor, left has at height 2, 4, right is at height 2. So 4 minus 2, 2. So which is critical node? 70 is the critical node. Why it became critical node? Because of insertion of 32. Where you have inserted 32? To the left of left. So 70 is the critical node. Critical node is always A, B, C. So 60 is B, 40 is C. Now you can just relate both. Now B becomes parent. So you have inserted 32 to the left of left. It need not to be immediately connected. Somewhere in the bottom, load increased at left's left. So A became imbalanced. So here we do L rotation. Whenever you do L rotation, what happens? 60 becomes root, B becomes root, A and A right will be as it is, 70, 80, 75, 82. C left and right will be as it is. Now this is B right. B right would be A's left. So here just cut there, paste here, something like this. That's all. Now you check the balance factors. 0, 0, 0, 0, 0, 0, 0, 0, 2 minus 1, 1, 1, 2, 3, 3 minus 3, 0. Now all the balance factors are in the range minus 1, 0, plus 1. So it is balanced. So earlier we have got an imbalanced BST. Now it became balanced. So this is how LL rotation is performed. Similarly, what is RR rotation? Now it is right skewed. B is having some left child, A is having some left subtree, C has its own left subtree and right subtree. A is the critical node. Critical node we always consider as A. So the load is towards right of right. So here we do RR rotation. Whenever you do RR, though it is RR, we will represent with left arrow. So B becomes root, A will be left child, just like it is a mirrored rotation for LL. Just if you see LL rotation in the mirror, what you feel, that is what RR rotation. So C will not change. Now B left will be on B left side only as A's right. This is what RR rotation. So quickly, if you take some example, something like 18, 20, 30, 15, 19, 34, 22, 10, 32. Suppose this is the given tree. If you see the balance factors, leaf nodes balance factors are 0. Sheikh Kumar, because they are inserted in the left only, no? 15 balance factor is 1, 19 balance factor minus 1, 30 balance factor minus 1, 34 balance factor is 1, 24 balance factor minus 1, 18 balance factor is 1, 2 minus 1, 2, 3, 4, 2 minus 4 minus 2. So 18 becomes critical node. So whichever is critical, you take it as A, its immediate descendant B, its immediate descendant C. Now 32 you have inserted towards the right side of right side, somewhere in the bottom. So we are not considering from 32 point of view. We are always considering from critical node point of view. So let's take this example. As the load is towards right of right, here we do RR rotation. RR rotation. Whenever you do RR rotation, what happens? B becomes parent. B left will not change. A and A left will not change. They will be as it is. C and C right will not change. C left and right will not change. That also will be as it is. B left becomes, this is B left. It will be on the B left side only. Now also this is B now. This is A. This is C. But as A right. So just cut there and paste here. So after RR rotation, this is what? The resultant tree. You see the balance factors 0, 0, 0, 0, 1, minus 1, 0, minus 1, 1, 2, 3, minus 3, 0. So all the balance factors are in the range minus 1, 0, plus 1. Hence it is balanced. So to make an unbalanced tree to balanced, we can use LL rotation, RR rotation. Now let us see LR rotation. Okay. LR rotation, you observe, if B is left child of A, C is right child of B, A is becoming the critical node. When we wanted to do LR rotation, first we do right rotation. That means first we do RR rotation. Then A becomes, C becomes parent, B becomes left child. Then you do LL rotation at A. Now C becomes parent, A becomes right, B becomes left. So LR rotation is a single rotation, but performed in 2 steps. It is not counted as 2 rotations. It is counted as a single rotation performed in 2 steps. So the same, let me tell you in short. So if you wanted to do LR rotation, what happened? C became parent. C came to A place, A went to right, B is left. So you can perform this in 1 step also as a shortcut. Okay. Now, if you take the general model for LR rotation, A has some right subtree. Its left child is B. B has some left subtree. Its right child is C. C has its own left subtree and right subtree. A is the critical node. Whenever you do LR rotation, directly how you can write? C becomes parent. What Santanu Sahu? In case of LR, first is left rotation, then right rotation. First we are doing right rotation, then left rotation. Okay. C becomes parent. And you observe this. B will be as it is. So B and B left will not change. A becomes right to C. Now we have to include C left, C right. C left will be on the left side of C only, but as B's right. C right will be on the right side of C only, but as A left. So in general, you can use this. So if you understand the standard method for every rotation, any rotation you can do. So what is the skill? Finding A, B, C. So this is LR rotation. Now finally RL rotation. This is again mirrored rotation for LR. B is the right child for A, C is the left child for B. A is the critical node. Again, this is a two-step rotation, but considered as single rotation. Here first you do left rotation. So C becomes parent. Then you do right rotation. Yeah. Now C becomes parent. A will be left, B will be right. So in one step you can write this as whenever you do RL rotation, C should come to A place. A should become left child, B should be the right child. So we can have a standard. B has its own right subtree, A has its own left subtree, C has its own left and right subtrees. A is the critical node. Whenever you do RL rotation, C should become parent, A will be the left child, B will be the right child, C left would be on C left only as A right, C right would be on C right only as B left. So for understanding AVL rotations, this is what very important. Okay. Santan Sahu, no question of first left, second right, first right, second left, forget that. Just follow this shortcut. I am telling the shortcut. In one step you can do LR rotation, RL rotation also. This one. For LR, first right, then left. For RL, first left, then right. Okay. So now guys, this is one model question. Which of the following is not a critical node in the given BST with elements so and so? It is a binary search tree. So first node we will always take it as root node. 8 is smaller than 12, so it is left child. 18 greater than 12, so it is right child. 5 is less than 12, less than 8, so it is left child. 11 is less than 12, greater than 8. Like this, if you keep inserting, this is the way. This is how you will get the tree. Now what is not a critical node? Find the balance factors. 0, 1, 2, 2, 1, 4 minus 2, 2. So which has balance factors other than 0, minus 1, plus 1? Sheikh Umar, in RL we will do first left then right. In LR, reverse, you have to think in reverse. In LR, first right then left. So here critical nodes are 12, 8, 5. So 12 is a critical node, 5 is a critical node, 8 is a critical node. We want which is not a critical node. 11 is not a critical node. Right? Very good. Guys who are confused about this LR RL, just find the shortcut, follow the shortcut that I have given. Don't think much. When you have a short way, why you will mess in the long path? Next, dash number of rotations required to insert a sequence of elements into an empty AVL tree. So first we will insert 9, whose balance factor is 0, only one node. Then insert 6. Balance factor of 6 is 0, 9 is 1, balanced. Insert 5. Balance factor of 5 is 0, 6 is 1, 9 is 2. So now you will understand, guys. Now you understand what is A. Critical node is always A. B. What you have inserted? 5 you have inserted. Where you have inserted? To the left of left. Until 5 is inserted, 9 is balanced. Once 5 is inserted, 9 became imbalanced. So the load increased where? To the left side of left. So here what you do? LL rotation. So we have identified A, B, C. A, B, C. So make B as parent, A as right child, C as left child. Now balance factors are 0, balanced. Now insert 8, 6, 5, 9, 8. Balance factors 0, 0, 1, 1 minus 2, minus 1. Balanced. Balanced means what? Minus 1, 0, plus 1. In this range the balance factors should be. Now insert 7. So if you insert 7, where you insert 7? As left child of 8. You see the balance factor? 0, 1, 2, 0, 1 minus 3, minus 2. Now you listen carefully. Whenever you have multiple critical nodes, always, whenever you have multiple critical nodes, always balance from bottom. Balance from bottom critical node. So give priority for the bottom node. Automatically top node becomes balanced. So here 9 is critical, 6 is critical. So which one we will take as A? 6 or 9? 9. So when this is A, this becomes B, this becomes C. So A, B, C is only the parameter constraint for us. So to the left of left, 7 inserted where? To the left of critical node left side, left side. So do LL rotation. So don't touch anything other in the tree. Only that ABC part you have to verify. So now B become parent. Make B as parent. A को right बनाओ, C को left बनाओ. हो गया. You see the balance factors now. Balanced. Now insert 10. Where you insert 10? Here you insert 10. Check the balance factors. 0, 0, minus 1, 1 minus 2, minus 1, 1 minus 3, minus 2. Now 6 is critical. Now you see guys. 6 became critical. Why? What you have inserted now? Till now it is not critical. Now only it became critical. Why? Where you have inserted, what you have inserted? I have inserted a 10 to the right of right. To the right of right. So when 6 is critical, 6 is A, 8 is B, 9 is C. So what rotation you perform? RR rotation. Now B becomes parent. B becomes parent. So 8 will be parent. Recall the standard method. A को left करो. A will not change. C will not change. C and its children will remain as it is. Now B left will be on B left only as A right. Done. Now you see the balance factors. All are balanced. So how many rotations we have done? Total 3 rotations we have done. 2 LL rotations, 1 RR rotation. Santanu Sahu, no. 1 LR, 1 RL considered as 1 rotation. 1 rotation only. It is considered as 1 rotation only, done in 2 steps. Srishti, no. Single rotation, double rotation. Double rotation is not counted as 2 rotations. Double rotation is considered as 1 rotation in 2 steps. Okay. Now, guys, we are happy to announce that in top 100, 60 plus students have achieved AIR in top 100, like CS 4th rank, CS 20th rank, CS 39th rank, 39th rank, 47th rank. So next time I want to see you all. So prepare well, guys, and take Gradeup Super subscription and enjoy all structured live courses taught by expert faculty. Get all your doubts resolved and full syllabus coverage. Get the green card to access all online mock tests which are all designed by toppers. Guys, you try this. Okay, you try this. Take the screenshot and try this. So I'll count 5 for the screenshot. 5, 4, 3, 2, 1. Mingma, currently I cannot comment because I have not gone to the statistics. Maybe once I go through the statistics, I will be able to comment on that properly. I just don't want to comment randomly on such great net exam. Let me go through the statistics, then I can give you proper comment. And guys, for all my classes information, download Gradeup app and follow me on Gradeup app. That's all for today. I hope your AVL trees concept became more and more strong now. So keep attending the sessions and keep sharing the sessions. Don't forget to like, share and subscribe to Gradeup Gate channel. Thank you guys. See you on Monday with the topic magnetic disk, which is from computer organization and architecture, operating systems. For in both subjects we have this common topic. That's why I have picked it as important. Okay. Thank you guys. Good night everyone. And guys, before I let you go, we are very proud to say Gradeup is celebrating 5th year anniversary sale. As a token of that, there is a huge discount on the subscription fee, you can see. So hurry up and get the subscription. Recommend our Gradeup Super subscription. Thank you. Prep smart, score better, go Gradeup. Thank you.